Hello, hello. Hello, Sarah. Hello, Jose. Hello, Ashley. Hello, Miriam. Hello. Hi, hi, Kay. Hi, Ashley. Hi, Brianna. Oh, that's an actual in-person Brianna. That's awesome. Hello, Ash. I said, yes. Hello, hello, Stephen. Hi, Sarah. Hi, uh, hello, Stephen. Did I say Stephen? Sorry. Hello, Stephen. Huh. Hello, Jose. Oh, hello, my board that just broke again. Why is this? Excuse me. Hello. Hi, Alejandro. Oh, fair enough. Okay. Hello, direct chat person. I totally understand. That's hi, Jasmine. Did I say hello, Alejandro? Hello, Jose. Hi, Sarah. Okay, I'm going backwards now. Hello, Stephen. Hello, Ashley. Hello, Kay. Hello, Miriam. And wait, and good afternoon, Katya. Okay, we're gonna and hi, Montserrat. Sorry. And hi, my board that keeps falling off. I mean, falling off the, you know what I mean. Top of the afternoon, Abdel. Oh my God. Oh my God was not at Abdel. It's at my board. Okay. Okay. So we're gonna start. Oh, and hello, Tobias, who's in the I think. Wait. Yes. Okay. And where's my okay. Okay. All right. We're gonna get right down to again. Yes, I was just about to address. Yes. Okay. I was just about, no, there's something in the direct chat. I totally, oh my God, my board just went again. Sorry, I don't know why this keeps. Okay, so there are some of you that's, I think it's not most, some of you still have not received a midterm exam grade. That is true. That is my, sorry. Hello, Gianna. Hello, Brian. I think most of you have. I like to believe that most of you have. Some people have still not gotten a midterm grade back yet. That is my fault, and I apologize. They're coming in very slowly. They're still coming in. I certainly haven't stopped grading them or anything like that. If you haven't gotten one back yet, certainly please forgive me. I mean, please stand by. It's coming. Please don't take it personally. It has nothing to do with you personally. There's one little thing though that I have. The board. Sorry. One little thing that is going on with some of your exams, not all. And again, this also is not a personal thing. There are some exams it's taken me so long, but I'm noticing that now that even though any document should work at this point, like Google Docs should work and so forth, but I am noticing there are some exams where I can see the exam there. I can see that it came in on time. In some cases, I can even see that it looks like really neat, clear work. But some of them, even though I can see it, for whatever reason, I cannot upload it at all on my side in order to do the comments. Generally, if I'm having that problem, I'm writing the person personally. Like some of you might have gotten personal notes from me recently, not personal, but I mean direct messages from me personally that say, I'm so sorry. I see that your exam's been here forever, but I can't get at it for whatever reason. If so, please. So if you've gotten one of those notes from me, or even if you just think there's the slightest chance, like if you used a Google Doc or a Word doc, even though that should work, they seem to not be working sometimes. So if you still haven't gotten one back yet, it is not a criticism of you. It is my fault. But if you want to check, and maybe if you can please re-upload as a PDF, don't erase your other exam or anything, like leave it there so I could still see that you were totally on time and all of that. But if you can upload a PDF, in some cases that will help a lot. They're a lot easier to grade for whatever reason, or a lot easier to mark up. That's not the case in all of you. Some cases it's just my fault and there's no reason. But in some cases I can't get at the document but please just bear with me if you still haven't gotten a grade. That is true of some of you. And I apologize. I think most of you have, and they're still coming. Oh, okay. Thank you. Oh, okay. So maybe that's okay. Thank you, direct chat. I totally see. Wait. If it was a PDF, you probably don't. And I do. Right. I'm seeing the direct chat. if you submit it as a PDF, then I don't think that's the issue, and you don't have to worry. And I mean, right. And just bear with me, and I apologize. But if there's any doubt in your mind, or you did submit as a Google Doc, if you can submit as PDF, that would help. But right, again, this is not, and good afternoon, direct chat people. Okay. So, and just keep bearing with me. I apologize. Again, I think most of you have them, but some of you definitely don't. And it's not a reflection on anything but me, but also to all of you now. And I do want to get back to material in a second. This problem that I assigned last Wednesday, let me back up again. There's no new homework for you're done with any new homework for the rest of the semester. The only thing that's left for the semester is everybody catching up on anything, like me catching up on your exams, or you catching up on any old things that you want to still turn in for points, which I'm noticing that some people are doing, and that's great. And then we're going to get to the final exam. We'll start talking about that very soon. Like we'll start talking about it this Wednesday, I suppose, but correct me if I'm wrong. We still, wait a minute. Wait, today's the, actually, wait, you better, wait a minute. We have this Wednesday, correct me if I'm wrong in the chat. And I know the board is gone. The board will come back up in a second. We have this Wednesday. We have next Monday. And then is that our last, is next Monday our last? Yeah. Oh, yes. Okay.
Yes,
okay.
Professor.
Thank you. Oh, thank you. Thank you. Okay. Wednesday and Monday is off. Right. Okay. That is what I thought. Just making sure. Okay. So yes. So then we'll talk about, so mostly Monday of next week is when we'll totally talk about the final exam. You will, prior to then, you will have gotten a practice exam for it. We'll talk about all this on Wednesday, and the final exam is going to be shorter too than the midterm, especially because, I mean, there's a little bit of a backlog here. But we'll talk about all of that. But but why I'm saying all of that is that the problem that I assigned last Wednesday, it is for optional points for any and all of you, points to go back on your midterm grade, even if you haven't gotten one yet. It's obviously open to anybody. It's due Wednesday at midnight. I mean, this coming Wednesday at midnight. One person wrote me so I signed it. I went over the whole solution, I believe, in your class on Wednesday, but it's true. Somebody wrote me. They had two good questions that they wrote me about. Let me try to be clear about this. I might have to put the board back on and this won't affect your points or anything like that, but two good questions. One is in the problem that was assigned last Wednesday, that's for extra credit points to go back on your midterm score. In the problem, I said that there was a force pulling up on the block with 200 newtons of force. Then when I solved the problem, it seems that somehow I wrote in 300 instead of 200. That's my bad. And I apologize. That's true. Someone pointed that out. That's a mistake. So, I mean, the number should have stayed as 200. That I just switched it to 300 is my mistake. So please be aware of that when you do the problem and hand it in. If you haven't already, you can, if it makes it easier, you could just change the original number from the original problem to 300 if you want, like whichever is easier for you to do, so you can just keep my consistent solution. That's totally fine. It was just a miscopy that I went from 200 to 300. I hope you're understanding what I'm saying. In fact, I'm just going to pause there. Can you just do electronic hands if you understood what I just said about 200 and 300? Great. Thank you. Okay. Awesome. Thank you. Okay. Awesome. And I see that one. Great. All right. Thank you. So just, yeah, I don't want to make a big deal of it or like, great. Okay. So that's, and then honestly, I'm now aware of it because one person, thank you, one of the people that is raising their hand, brought it to my attention. That means also I'll just be, even if someone didn't hear me right now, if they wrote the problem as 300, but then they solved for 200, like that's obviously my bad. But one other thing just to say about that, I'm going to try to say quickly, you're going to see again in today's problem, I think, or you saw, well, sort of, and you saw in the lab, sort of, as far as pluses and minus signs, plus signs and minus signs are decided by coordinate system for sure. In today's class is like a lot about coordinate system choices for sure. So if we decide in a coordinate system that up is positive, for example, and down is negative, then that means every force in your free body diagram, every force arrow that's pointing up would then get a positive sign in the equation F net equals MA. And every arrow that's pointing down will get a negative sign in the equation F net equals MA. All true. And again, I'm saying this because it's an important point, and also because at least one person should have raised this really good question outside of class. So that's all true. But now let me try to say this as clearly as possible. If you say that down is negative, then the force of mg, the arrow that designates mg, the weight of an object, then for sure that force mg will get a negative sign on it when you're doing out Newton's second law. Like you would say, you'd say minus mg for sure. But that's it. The force of weight would be negative, would point down. Mg means mass times the free fall acceleration due to gravity, the 9.8 number. Mg, your weight, means your mass times that 9.8 number. If we're calling, and your weight always pulls you down. So if we're calling down negative, then for sure you put a negative sign before the mg. But what I'm trying to say very explicitly to everyone, because this does confuse people like every semester, you would put a negative sign before the term mg to make sure that that whole force is pulling you down negatively. But that's it. You don't want to double psych yourself. You don't want to double count yourself and accidentally make it a negative times a negative, which would be a positive. So in other words, my punchline is G, lowercase g, the number G is always just the number, like 9.8 meters per second squared, or if we're rounding 10 meters per second squared. The G from here on in life never gets a negative sign anymore. Negatives or positives go on the whole force of mg, and they go on it once you've made a decision. We don't double count the negative. So in order to prevent double counts or confusions or redundancies or whatever, lowercase g from now on is literally a number, just the number. And if we're doing a problem like today's where we're not even substituting in numbers and we're just leaving everything as letters, then g just gets left as the letter g. It itself is not negative. It stays as g, and the whole force mg will get a negative sign if and when we're calling down negative. So I believe that applies to the solution to the extra credit problem that you're turning in for Wednesday at midnight. I'm going to pause for a second. I'm going to turn to a new problem in a moment and talk about it. But I'm going to pause for a second and look. Oh, I'm going to get my board back hooked up again. But also, as I say, there's at least one person that raised my awareness of that issue, and I'm very glad he or she did. If that person knows who I'm talking about, if they could tell me in direct chat whether I understood the question properly and whether I've just addressed it, like that would be helpful, because I might have misunderstood what their question was, but I think that was it. And if they're hearing me right now, if they could tell me in direct chat whether that like addressed it, that would be great. Okay. Right. Exactly. So direct chat person, yeah, exactly. So thank you, and yes, and that would count as closing our conversation, but yes, exactly. All right, I'm gonna, right, oh, yes, that's true. And if I blew that in the solution, then I'd like to know, but I don't think I did I? Sorry, I'm talking to the direct chat person right now, but yes, I'm agreeing with, I'm going to get my board working while this is happening, but yeah, so now maybe I should look back to are we on the same page? Or sorry, this is like, so I'm going to get my board back working, but direct chat person, I'm agreeing with everything the direct chat person is saying, but I'm not sure if they're agreeing with my agreement with their agreement. Like, or I'm not, here's what I want to know from Okay. I'll look too then. So okay. I'll look. All right, I'm gonna get, but fair enough. I appreciate your honesty and thoroughness. And I'll look too. I am gonna, but right now I'm gonna get the board going, which also means I could look. Yeah, all right. Pardon me, everybody. I'm gonna get the. Yeah, please do look, because I don't think I made a mistake there. I definitely made a mistake with the 200, 300 thing. But okay, so you'll look. All right, so I'm gonna get the board going. I don't know why this board, and then it'll die again. Okay. Wait, MG is gone. Wait, all right. And I'm gonna pause for a second. The board. Okay, this is a word. So obviously somebody is asking a question, and it's a very valuable question. I don't mean to be so cryptic and so like cagey about direct chat, this and that, but it's a very good question someone's raising. So the board should be going up. Yeah, and if it, all right, I'm going to take a moment now. And also because this is points for all of you. So let me make sure I'm going to right now to all of you. I'm going to go back to, I'm going to look at the notes publicly from what we did last Wednesday to make sure it's as unconfusing or as correct as possible. Because again, like you can all get points from this, so we might as well be. So bear with me for a second, everybody. If you understand what I'm. Hold on. Okay, no, this is worth. All right, we're going to talk about this right now because I think I see where I think I see where the confusion is. Okay, first of all, to everybody. So right now you see on your screen, I hope you see on your screen, this is the problem from last Wednesday. Again, for anybody who's just tuning in now, no. Yeah. No. This is not inconvenient. Like this is worth it. And all of you, seriously, like class is supposed to be this way. I mean, I'm going to sound spazzy no matter what's going on. I mean, I think many of you know that at this point. And I'm going to be, and we're all going to be together for Physics 204 again. The more I can be here to actually address things that you guys are thinking, the more of a class it is. Really, like, and that's, it's harder on Zoom, but no, but I'm going to sound spazzy no matter what. And even if it's only one person who's asking this, that doesn't mean that a lot of other people aren't benefiting from it. And also, one person asking a question is better than zero. I mean, it's better than if I'm just in my head. So no, this is worth it. So and plus, it's points for all of you. Like so what I'm going to do right now. So again, so what I mean that. But my board just disappeared. That is. Good God, I don't know why that, but what I'm trying to do for everybody right now, even if it just like takes a couple of minutes, I'm taking the problem that we went over on Wednesday, and I'm saying again, like, because you all have till midnight Wednesday night to get a lot of points for resubmitting this problem, right? So one thing I'm going to do right now is the number in the problem says 300. I'm going to right now publicly change it to 200 so that the solution is right and so that there's no issue with that. But then I'm going to look at this other thing that this person is talking about, because that whereas I don't think it's actually a mistake on my part. I definitely understand why it's it's like a confusing, it's like a worthwhile idea. Okay, so here comes the board again. God knows how long it'll stay. Okay, so first of all, here's the problem right here that I'm talking about to everybody. Again, you have till Wednesday midnight to do this for like a lot of points on your exam. I think I said 8, and like maybe it's even more, but I think I said 8, and I'll definitely stand by at least whatever I said. So one thing I'm going to do right now, just to make this clear, it says 200 newtons. Let's just right now change that to 300 newtons, just because like when I solved it, apparently I used 300. So, okay, so I'm changing. So that's okay. So first of all, can I just get a show of hands if that's clear? I'm just changing. And if you already turned it in, don't worry about it. It's fine. But okay, cool. Okay, great. Okay, so that's that. Now, that's like my typo. But now here's this other thing that the person in direct chat is talking about. Totally worth, and it will relate to what we're doing today. Like, okay, so here I start. Remember, we're trying to solve for the acceleration. So I do all this thing with forces and all that. I mean, I do the system schema, then I do the pure free body diagram. Okay, so here's the system schema, then here's the pure free body diagram. A lot of forces going on there, right? I mean, it's definitely a sophisticated problem. And then I list all the action-reaction pairs here. Okay, then now we have to go to the component free body diagram, which is what really today's class is very much about. We're going to we choose axes so that we can break up each force into its components along the axes. And notice when we choose axes, we literally say, okay, we're choosing that this is our y-axis and that up along the y-axis is positive, and this is our x-axis, and to the right we're choosing as positive. So I'm saying this is really a choice. Like, we're choosing what do we mean by y, what do we mean by x, and we're choosing what do we mean by positive, what do we mean by negative. There's lots of, you're going to see today, not as obvious a choice as it might seem, but whatever it is, whether it's obvious or not, it's necessary. There's more than one possible choice, and we have to, it's not that we have to make any particular choice, it's that we have to make some kind of choice, and then we have to stick with it. So, okay, but so we do that, we did that, then we designated, so here's where the direct chat person, oh my God, and the board just failed again. Sorry. But here, this is about to disappear because the board just failed. But you see, we chose up as positive, we chose down as negative on the y-axis, right? So that means that arrow that's pointing down for mg is going to get a negative sign in it when we add up all those forces on the y-axis and do F net equals ma. But now, what page is that? Page 11. It's about to go away again. I'm going to bring it back. But now, where he's asking, or he or she is asking, is so here comes the board back again. I don't know why. Okay. So we make these choices. We say up is positive, down is negative. And we say independently, but simultaneously, to the right is positive, to the left is negative. And so then the whole purpose of why we did all of this work, and again, you're going to see this in a harder application today, the whole reason for why we made all these arrows, when we broke them up into just purely X arrows and purely Y arrows, is so that then we could expand the left side of F net equals ma, and we could say, okay, the sum of all of the X forces equals the mass times the acceleration in the X axis. So we look at that picture on the prior page, and we say, okay, in the x-axis, there's t cosine theta going to the right. We're going to add that to the friction, but the friction's going to the left, so friction's going to get a minus sign, right? Like, it looks like I'm saying t cosine theta minus friction. I mean, in a way, that is ultimately what I'm saying. But where did I get that? I'm always just adding everything up, but everything that's going in a negative direction is getting a negative sign. Okay, so friction got a negative sign. Now, friction is always, and we learned this last Wednesday, friction is always the coefficient of frictionness, the roughness, mu, times the normal force between the two surfaces. In other words, the friction between two surfaces is always how hard they're pressing together, normal force, times how rough they are, mu. Okay, so friction is mu times the normal there. So I substitute in mu times the normal for friction, but the negative sign was like already there. So I just like substituted mu times the normal for friction, right? And I just leave normal as normal because I still don't know it. I don't know what the normal force is. There's no formula to memorize or anything like that. How can I find out? And I'm trying to solve for A in the X direction. I'm trying to solve for A, but what's unknown is N. What's unknown is A, but what's also unknown is N. So that seems like a problem. It seems like I've got one equation with two unknowns. I need another equation. where am I going to get another equation? Especially where am I going to get an equation that has the normal force in it? I look to the other axis. This is one of the reasons that we divide everything up into axes, because each axis provides its own independent but simultaneous set of forces and acceleration. Each axis provides its own equation and therefore its own information to solve for unknowns. So I go to the next page to the y-axis. Now here's where I think, oh yes, I see where, I believe I see where, and again, this is to everybody. This is not just, yes, one person brought this to my attention, but that's because like they're being a student, which is good. So now I'm talking to all, like, I think this is much more valuable than anything that I could just like babble about. Like we now, and by the way, this type of problem is generally on the final exam. So this, I mean, not to be weird, but I promise this is not a digression. Like this is the class material. So if we go to the y-axis now, we go to the y-axis and we look at all the arrows going up and down. Right, wait, I'm looking at the direct chat. So yeah, I'm going to keep talking, but let me just see. Right, exactly. Direct chat person. Right, I'm still going to say it my way, but yeah, that's the point. Yeah, okay, cool. Right. We're trying to prevent double count. Right. So now I go to the y-axis and I'm just adding up all the arrows in the y-axis. I've got a t, and there's three of them. There's t sine theta, there's the normal force, there's mg. Those are all forces in the y-axis that are all getting added together, but mg is down. So in this addition, it gets a minus sign. Like technically what's really happening here, everybody, and there are different styles for doing this. Like this is not, I'm not saying this is the only way, but it is certainly a consistent and I think simplest way. What we're really saying is this. We're adding up all the forces, but since mg points down, which we're calling the negative direction, it's getting a negative sign. So it's technically, right, it's a plus of a negative, but that means it's minus. And this is what I do all the time. In other words, to everybody, I'm not putting a negative on the G. G is just a number always. So not like your weight is your weight. Your weight is mg. You weigh 220 newtons or whatever. Like, and that means by definition always that 220 newtons of force are pulling you down. Okay, so I have like, so this is what I'm saying. But your acceleration along the y-axis in this problem, in this case, where a block is just being dragged horizontally along the table, it's not accelerating upward. And by the way, I know that the direct chat person is now satisfied. I'm not like yelling at him or her. I'm not yelling at anybody. I'm just like excited because it's physics. Like I get that, but I'm just like finishing this for everybody. I'm now saying, okay, since the whole left side equals 0, since there's no acceleration in the y direction, then I can bring that mg to the other side because it had a subtract, because it had a minus sign. So I say t sine theta plus n equals mg. So therefore, I can solve for n. N equals mg minus t sine theta. That's a complicated expression. But why did I even care? Why am I going through all that? Like I'm saying, the normal force of the table has to support a little bit less than the weight of the object. Why less? Because some of the weight of the object is already being pulled up somewhat by that string, by the vertical component of the string. So n equals mg minus t sine theta. I care about what the normal force is because it gets plugged back in for that expression for friction. Friction is mu times the normal. So it gets plugged back in, and in that plug back in, the mg is still positive here because we weight is like the magnitude of the weight is still positive because we've taken the direction of the force into account all the way along. Like it ended up on the right side of our equation because it was negative on the left side. So now it's positive on the right side. So anyway, so this is where it looks, or it looked like, at least to one person, like somehow I wasn't treating gravity properly. But gravity is being treated properly here. And so we get t cosine theta equals mu. We finally get at the bottom. T cosine theta minus mu quantity mg minus t sine theta equals max. Ax is what we're solving for. So then I just divide both sides by m, and then I plug in all the numbers. This is where I plugged in 300 accidentally instead of 200. So I just changed the problem to 200, and that's how you do it. Okay, so that's from last week. That again, anybody, again, practice, use this. Some of you, by the way, really like, I appreciate have asked me like, can I have some more tips or like things that I can do for the final exam? And I'm trying to tell people some things that they could do better for the final exam. But one, and you know, it's different specific things for different people. But one thing to all of you, just please, I know it's a funny course. It's a funny, I mean, physics is funny and I'm funny, ha ha. But one thing just to remind all of you, physics is more, studying physics really, in my way of thinking, is more like studying math, or more like studying French or Spanish or Chinese or piano, for that matter, than it is like studying bio. Like those of you who get thrown because you've been having your science hat on for years and have really worked up your science student skills as, you know, as impressively as you have, you can get thrown in physics because suddenly physics doesn't feel like a science in certain ways. It doesn't feel like bio or even chem sometimes. One way in which it's different is it's not about knowledge accumulation. There's very little to know in physics, surprisingly. What there is a skill to be practiced. So one thing I just want to say to all, one reason this is worth me going over again right now, and why it's worth me assigning to you for extra points, even if I'm giving you the solution right here, and I know that I am, is the best thing you can do between now and the final exam is practice doing these things just over and over, even doing things that you think you already know how to do, or that you think I gave you the solution for. If you try to solve this problem without looking a couple of times, and then when you get stuck, look, like every time you get stuck, fine, look, but then realize that you had to look. So you don't know the problem that well if you have to look. So sort of keep practicing it and doing it out until you don't have to look anymore. And once you don't have to look, do that version as the thing that you hand into me, because I promise you, by the time you've done this enough times with looking, then when you finally do it without looking, it is going to be your original work. It won't be a copy of the way I do it. And I will be able to see the difference. And that's what you do want to practice for your final exam. Just honestly, and I'm going to move on. But some of you who got slightly lower scores than you expected or than you would want, even though you feel like you knew what was going on or you had the answers in front of you and stuff, the truth is you got to ask yourself in your heart, did you ever do the practice exam really ever all the way through without looking? And that's not an accusation, but ask yourself in your heart, you know the answer. Did you ever do the practice exam really ever once without looking? If you didn't, no shame, but that's the first thing you want to really do before the final exam. Like when you get the practice exam, keep doing it until you can do it without looking. You might think, well, why do I need to? I've got the answers that I can look at when I turn in the final exam. But the reason is, if you're looking at the answers when you do your final draft, you don't know it as well. And it's not you talking to me, it's me talking back to me. This is much more about practicing the art of physics than it is about, so short story long, for those of you who want to like raise your scores or whatever, or still worried about your for the final exam, really, when you get the practice, which you will soon, just keep trying to do it without looking. And then every time you have to look, fine, you can look and you can get the answer straightened out because I'm giving you solutions. But your goal is to get to the point of doing it without having to look. All right, enough of that. But hopefully anyway, this all just happened because I think this is now correct. Hopefully the gravity thing maybe addressed that one person or other people. This is the procedure for how you solve these kind of problems. Now I'm going to turn to another problem, one step more difficult than this, very similar to what you did in the lab. Hopefully your lab experience will help, but I'm going to turn that, and this problem that I'm going to do, usually often some version of it is on the final exam. So I'm going to, if there's no, I mean, stop me in the chat or whatever, if anything is unclear, whatever, but I'm going to switch pages now and go to today's thing. Okay. Oh, it stopped again, of course. So Hold on, the board's coming back. So frustrating. Okay. I know the board is frozen. I knew, okay. Okay. So here's what we're going to do today now for the whatever time. Yeah. All right. We've got the issue today. This is going to look a lot like the lab situation. Now, again, we're going to have a block on a rough surface, just like that last problem. Only now, instead of pulling the block at some angle, the surface itself is going to be angled like the lab. This is now a rough inclined plane. We're going to have a block sliding down a rough inclined plane, block of mass M, inclined plane of roughness coefficient mu, and angled from the horizontal at some angle theta, again, like the lab. The goal here, again, just like the last problem, the goal is to compute the acceleration of the block on the inclined plane. Ultimately, I would like the acceleration of the block, whether it's going down or even if it's accelerating or even if it's moving up. You know, both of those things happened in your lab, in lab 5, right? You sent a block up an inclined plane, it went to some height and then it fell back down. And your whole goal of the lab was to compare the accelerations one direction versus the other, and they were different. I would like to get the accelerations, or at least I would like to get the acceleration for the block coming down and even for the acceleration going up so we can compare them. But kind of like for some of the lab, so this problem is like the last one, and the procedure will be like the last one. Like we're going to do a system schema, we're going to do a pure free body diagram, we're going to divide up the forces and get components, do a component free body diagram, and then plug into F net equals ma and solve for A. Standard Newtonian procedure. Couple of things that make this problem a little bit harder than the last one. Number one, I'm not even worrying about numbers anymore. We're sort of done with numbers now. We're going into real physics here, and it's going to be like this a lot in Physics 204. When I say I want to solve the acceleration here, I'm not even going to get a number for acceleration. I'm going to get a acceleration as a function of the given constants, the given values of mass, free fall acceleration due to gravity, theta, and mu. Like, so I'm going to get, my final answer is not going to be a number. It's going to be an algebraic expression that shows how A depends on those known measurable lab quantities, such as mass, mu, and theta. One thing, if you, so this is going to be, a lot is going to be, so number one, it's harder because there's no numbers. Number two, here, you're going to see it's a little bit harder because now the surface itself is tilted. The direction of the acceleration itself is now tilted. That's going to make a difference as it did in the lab. It'll cause us to think a little bit more in our analysis, but we will. And that's what we're going to do in a minute. Just a warning: you might you might know from the you might know the following from the lab. But I say we're going to look. Our goal is to get A. Like the question is, what is A? So if we're doing the 5-step problem solving method, like step 1, DFP, diagram and fact pattern. The diagram and fact pattern is the diagram that you're looking at right now, and those are the facts: the mass, the theta, the mu. Step 2, what is the question, WIQ? The question is, what's the acceleration down the plane in this case? Okay, now step 3, GDP, and step 4, particular application and work. To do those, I'm going to divide those steps of general definitions and procedures and particular application work. I'm going to divide those into step A, B, C, D, the general techniques that we do to solve a Newton's law problem. In other words, I'm going to make A, B, C, and D, like my system schema, my pure free body diagram, et cetera, et cetera. And finally, when I get a final answer, it's going to be an expression. It's not going to be a number. It's going to be a function of the knowns, mass, G, theta, and mu. To be super clear, because you might have seen this in lab, when I say it's a function of those knowns, that I'm going to get an expression that is in relation to mg, theta, and mu. what that means is I won't need any other information at all besides those facts. That as long as I have those facts to plug in as input, I would be able to get out acceleration as output. It means I don't need anything besides those inputs. It doesn't necessarily mean that I'll have to end up using all of those inputs. You might know from the lab, or you might have realized that, and I'm going to tell you right now, as a matter of fact, of all those input constants, the M, it turns out, is going to cancel out. I don't want to confuse anybody or trick anybody. As it turns out, we're not even going to have an M in our answer. It's going to cancel out. But that's going to be an interesting discovery to see that it cancels out. We wouldn't necessarily know that going in. And so when I say that A is a function of all those, what I mean is we're allowed to use any of those. If we end up not using them all, that's fine. It just means that we can't use anything else. Okay, so we're going to solve for the acceleration of a block on a rough inclined plane. This is a rough inclined plane. Okay, much like you did in the lab. All right, so our goal is to get the acceleration, and honestly, as was the case in the lab, you're going to want the acceleration up and the acceleration down, and see, as you found out in the lab, whether they're the same, or if not, which one is bigger. So here we go. Okay, so this is what, so again, this is just one step further, more sophisticated application of what we've been building for the last couple of weeks. So our goal is to solve for the acceleration of the block mass and sliding along the rough plane of friction coefficient mu, inclined at angle theta, and we're going to assume that we're in a lab, so we're at the surface of the Earth, so we're assuming that we know G. All right, that's just saying in English what we just said in the diagram before. This is all, so this is all like step 1 and step 2 here. Okay, so just a restatement of what you already know. All right, so I'm going to the next page. Now, I'm just making clear here too, as I already said, friction opposes the tendency towards motion. Like if the block is sliding down, friction is going to oppose that and push up. But if the block happens to be sliding up, friction is going to point down. So friction could do one of two things. Therefore, I think there's going to be two different cases here, and two different answers, an up case and a down case. So we just have to be clearly distinguishing them as we go. I'm going to focus on down because it's the easier thing. I'm going to focus on a situation where the block is sliding down. That's just sort of easier for most people to picture, but just recognize. So yeah, most of my work, I'm going to focus on down. But at the end of the day, if I want to know what's happening when the block slides up, I'm going to have to adjust for friction pointing the other direction. All right, so I'm just saying that on that page. So here we go with our customary procedure for Newton's laws problem solving. Again, if you missed anything on the last couple of pages, you could definitely put it in the chat, but all of that was just sort of a restatement of the facts of what we're trying to do here. So step A, right? This is all technically, this is all as far as problem solving, this is all steps 3, GDP, and step 4, PAW. So A is draw a system schema. So we're going to draw a system schema of the situation. We draw a dotted circle around the M, around the mass, right? We have a dotted circle there. Then we always have planet Earth anywhere we want in the diagram. I always put it up on purpose to demonstrate that direction is not something that we're learning from, or not something that we're communicating in the system schema. So I just put planet Earth somewhere. And then I put anything and everything that's touching the object. What's the only other thing that's touching the object? There's a plane here, meaning like the lab table or the surface that the block is on, a plane that happens to be tilted. Okay, the fact of its tilt is not in any way indicated by this picture, because this picture does not indicate direction. The purpose of the system schema is to identify all the objects that are in the world that are in any way interacting with our mass, because every object that is interacting with our mass is exerting a force on it. And the way we know all the objects that are interacting with our mass is we always put in planet Earth, and then we put in anything and everything touching our mass and anything and only things that are touching our mass besides planet Earth. So the table, or what I'm calling the plane, as in the inclined plane, as in the slide, that's touching our mass. So I drew a circle for it, plane. But then now I start connecting my objects with lines. First of all, planet Earth. So I always follow the one line, one touch rule. For every touch, I put one line. Every one line is supposed to represent a touch, but there are two exceptions to that. One is planet Earth never touches. It never gravitationally touches an object, but it's always gravitationally pulling on an object. So it just always gets a line, right? Planet Earth is always pulling on objects. So I put a line there from planet Earth, always, always. But then the plane is a surface that is pushing against the block. And so our other exception to the rule is whenever you have two surfaces pushing against each other, they always, especially if they're rough, they do so always in two ways. Remember, any surface that is pushing against another surface like that is also pushing against it like that, because the two surfaces, rough surfaces, interlock with each other. So whenever we have two surfaces pushing against each other, we always make two lines, right? And so we have that here, two lines, one that represents this phenomenon and the other that represents that phenomenon. One always accompanies the other when we have rough surfaces pressing on each other. So that got two lines. Now there's no other objects in this situation. In this respect, this is easier than last Wednesday's problem. Like last Wednesday, we had an object on a surface being pulled by Earth, but also being pulled by a string. There's no string in this situation. So that's it. Those are the only objects interacting with the mass. Even if you flick the mass up with your finger, you just did that temporarily just to send it up. You just gave the object like an initial velocity, V0, at the beginning, but that's not a force that is continually being applied throughout the mass's journey or at all throughout the experiment. So your finger is not part of this at all. Those are the total number of interactions depicted by the system schema. The whole purpose of that system schema was that by drawing our circles according to those rules, we generated or we found three lines in the system schema. That is the punchline, and the purpose of the system schema is that there's a total of three lines, three interactions. Therefore, there's going to be three arrows in our pure free body diagram. So now we're going to go to our pure free body diagram. One other thing it says at the bottom here of this page, this system schema, since it doesn't care about direction, it's only there to identify what the forces are. It does not care about direction. Therefore, whether the block happens to be sliding up or down does not change this picture. So that system schema is true for both cases. Okay, so that's that. We go to the next page. Now, we draw a pure free body diagram. Each one of those lines becomes an arrow in the free body diagram. Now I'm going to start distinguishing whether the block happens to be sliding up or sliding down. Let's say the block is sliding down. Right? Now remember the DFP, the step one, the picture that I drew right at the beginning of this whole problem on page one. I'm afraid if I scroll the pages right now, like I'm going to lose the board again. But if you look at that first page, my inclined plane happened to be drawn, mirror image, it happened to be drawn like this. I mean, right, if you look at the first page, the plane happened to be going like this. Now, you could draw it any way you want in that first page. I mean, a slide could be in a lap pointing that way, or it could be pointing the other way. But once I did draw it that way, one of the importances of that picture is it says from now on, I'm picturing a slide that is angled that way. So therefore, every free body diagram has to be consistent with that. So if that plane was going like that, that means that this is the plane. The block is on top of it. So the plane is pushing up and against the block. The against push, the component of push that is perpendicular to the plane of contact. Sorry, here's the, I can never do this because of the mirror. Right, the plane of contact is like that. The block is on the plane of contact. So the normal force pushes perpendicular to that. So my normal arrow is going up and to the left. Friction is along the plane. Friction is parallel to the plane of contact. So it points to the right. And why does friction point up and to the right? Because the block right now in this situation that we're investigating is sliding down. So friction points up and to the right. The normal force points up and to the left. And gravity, the weight, mg, as always, points down toward the center of the earth. So that's my pure free body diagram for the object when the object is sliding down. If the object is sliding down, then friction points up. Contrast that with the next page. If we were drawing a picture of the object sliding up, the normal force would stay the same. Like the plane is still the plane. Earth is still pulling straight down, but now friction would point down when the object is sliding up. Again, why would the object slide up? Because you flicked it, right? And it's continuing to go up until it runs out of steam. So this is the sliding down picture. This is the sliding up picture. Notice the only thing that changed in the two pictures was the friction force. Friction does that. Friction is the only thing that does that. Okay, so friction opposes the tendency towards motion. Now, so those are our free body diagrams. Now, again, I'm going to focus. I know we have 23 minutes. I'm going to focus. I want my analysis, my attention on the down picture. Everything I say is going to carry over to the up, except for that direction of friction. Like the one thing that's going to change is friction is going to flip its direction. We're going to focus on the down picture. When I say focus, in order to solve for acceleration, like our goal is to solve for acceleration. So what do? We've got to now use our picture to write out and expand and solve F net equals ma. We have F net equals, right? So we always do system schema to get the lines. We use the lines from the system schema to get the arrows in the free body diagram. Now we use the arrows to expand out F net and solve for ma. But the catch is this: F net equals ma is a vector equation. It applies independently yet simultaneously to one axis at a time. To say F net equals ma vector really is to say the sum of all the x forces equals the mass times the acceleration along the x-axis, while independently but simultaneously the sum of all the y forces equals the mass times the acceleration of the y-axis. And also, if there were a z-axis, which there often is, the same thing would apply to the z-axis. There doesn't happen to be a z-axis in this case. We just have, up and down, side to side in this inclined plane. But if there were a z-axis, same. So we have to look at the x-axis and the y-axis separately, and there can't be anything else but those axes. Any diagonal line we see, any diagonal force is going to be broken up into components lying along those coordinate axes. Now, so what we next do is we zoom in on the individual forces that look off axis, and we break them up into components that lie along the coordinate axes. That's what we do. And that's what you did in the lab. And that's what comes next. And that's what we did in the last problem last Wednesday. That's what we do next. But now here's where I'm going to sort of depart from what you did in the lab, or here's where it's at least not going to be where it's related, but it's not redundant. We have to break up forces now. We have to break up forces into sine and cosine. How to do that, which forces to pick, and how to pick whether it's sine or cosine is what tends to confuse people or at first, and definitely tends to confuse people like in that lab. In order to break forces up into axes that lie along, in order to break up forces into components that lie along axes, we have to choose our axes. That has to be a conscious choice. This is the whole Galileo thing. Just like in the river stream problem on the exam, you have to choose whether you're solving the problem from the perspective of the river or the perspective of the shore or the perspective of the boat. Any one of those choices would be correct, and the laws of physics would apply in any one of those choices. But you have to know which choice you've made and stay with that choice consistently. So you can make any choice, but you can't not make a choice, and you can't drift from one choice to another. So we have to make a choice here about what our axes are and what's positive and what's negative. Now you might, so the issue is positive and negative, yes, but more than that, it's what our axes are. This is where this gets very interesting and where things get confusing in the lab, or might have gotten confusing in the lab. I'm now going to first start, I'm going to do this 2 different ways in the next 25 to 19 minutes and also on Wednesday. I'm going to do this 2 different ways. I'm going to show you 2 different choices. They're both correct. One is natural and sort of seems obvious, but leads to a lot of work that you have to do. The other choice is less natural. It seems less obvious, and it doesn't even seem comfortable, but it leads to a lot less work. I want to show you both the choices. The first choice I'm going to show you now is, let's just assume that we don't do anything fancy, and we just assume that our XY axes are lined up with the lab. Let's assume first that we have an x-axis that points along the floor of the lab or parallel to the ceiling that lies along the horizon, i.e. a horizontal axis. And let's make the other axis line up and down with the line of gravity, make it vertical. Okay, let's, in other words, make the choice that seems so obvious you wouldn't think of it as a choice. We're going to do that first. I'm going to tell you right now before I turn the page. This choice seems so obvious that it may not even seem like a choice to you. But I'm going to tell you right now, it's not the choice that you made in the lab. It's not what you did in the lab, which is part of why the lab seems challenging or confusing at first. In other words, I'm going to, well, okay, so this all says, in order to find net fx and net fy, etc., we have to break our force vectors into components. In order to find components, we must choose coordinate axes. That's all of what I just said. We have to, like, honor Galileo. So we have to choose, okay? So let's say that first we choose a coordinate system oriented parallel with the lab itself. That's what I'm going to do right now. Now, again, this is not what you actually did in the lab. It seems so obvious, it may not seem like anything, but in fact, it's not what you did in the lab. Let's assume that y points straight up and down like this and call up positive and down negative. And let's assume that x points left and right, but I'm going to make left positive. This is not the big deal, but make left positive just because we have an inclined plane that's pointing that way. So the thing is going to slide down to the left. So I'll make left positive and right negative. You don't have to do that if you want. That's not the big issue, but I'm just going to do that. But the big issue is I'm lining up my coordinate axes with the lab itself, as opposed to tilting them along with the plane. So if I do that, oh God, it opened it. Why does it do that? Oh, sorry, I just lost the board again. And it's not my internet connection. It's definitely something with, I mean, who knows what it is. But okay, here it comes back again. I know I'm tracking at 16 minutes. I know. Okay. 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 So, okay. Now, if we use these as our axes, now it means we have to zoom in on every vector that is not pointing straight up or straight down. In other words, MG is now pointing straight down. So notice for this choice, I'm not messing with MG. I'm leaving MG alone, which, by the way, might have been what some of you might have preferred to do in the lab. I know in the lab you broke up MG, and I know that that's a bump for some of you. Some of you, it's a conscious bump, like what? And some of you don't even know that you consciously bumped over that. You just like accepted it because, you know, you're good people. But in the lab, when you did lab 5, you broke up MG, and that's a little weird because MG is pointing straight down. I'm going to explain why you did that. Right now, I'm saying, yeah, let's assume that we've got a coordinate system like this, and assume then that MG is fine. MG is not a problem, but the normal is off on a diagonal. It's off axis, and the friction is off on some diagonal. It's off axis. So let's assume. I know someone's here. I can't. Okay. So we've got to zoom in on the friction and the normal and break them up. Look to the right first at friction. Look to friction. It's going off along parallel to the plane. So the angle that friction is making with the horizontal is exactly the same thing as the angle that the plane is making. with the horizontal. In other words, that angle between F and the imaginary horizontal line is theta. Not just any old theta, but the theta that was given at the beginning of the problem. So F is going off at angle theta. So if I break up F into its two coordinate components, if I say that pointing up and to the right really means pointing somewhat up and somewhat right, means two different jobs, then I divide F into an adjacent side of that right triangle and a opposite side. The opposite is F sine theta. The adjacent is F cosine theta. Excuse me for one quick second. Okay, so I've got two, so I'm zooming in on the F. I'm getting its two components, F sine and F cosine theta. The reason for that is when I make a component diagram, I'm going to take out the F and I'm going to replace it instead with its two components that lie along axes so that I can do F net equals MA along each axis. But now I go over and look at the N. I don't know why I wrote them in, right to left instead of left to right, but it doesn't matter. But it's not meant to signify anything. I look at N. N's got to be broken up into two components, N cosine and N sine. But notice the theta in the N triangle is not, if I'm using that same theta to mean the original given theta, the angle of inclination of the original plane, it's not at the base of the left triangle because the normal force is not making that angle with respect to the horizontal. The normal force is perpendicular to the friction force. The normal force is not along the plane. It's complementary to the plane. It's perpendicular to the plane. So the angle that it's making to the horizontal is 90 degrees minus whatever the friction is making to the horizontal. So theta is actually up in the top left of that triangle. That's a little confusing. You may want to think about that. It's not a mistake, but it is subtle and you have to think about it maybe. So what's opposite that angle is down at the bottom, N sine. And what's adjacent to that angle, it's N cosine. Some of you might be thinking, and this again relates to the lab, you might be thinking, wait, I thought sine is always supposed to be vertical and cosine is always supposed to be horizontal. No, a lot of people think that. It's easy to think that at this point, and you're thinking that because of the way you originally learned sine and cosine with the unit circle. In the unit circle, that's true, that sine means the y coordinate and cosine means the x coordinate in the unit circle. But from that, what ultimately sine means opposite and cosine means adjacent. And it means opposite and adjacent to whatever angle you're looking at. So if we're writing this all out in terms of the original angle that we were originally given in the problem, then normal force gets divided into two components accordingly, like with sine at the bottom and and then friction gets divided the way it does. Now, what's the purpose of doing all this? And I am watching the clock. I know we've got 11 minutes. The purpose of zooming in on these is now we redraw our free body diagram. We draw it as components. So we're not going to have F in there any longer. We're not going to have N in there because they're diagonal lines that are off axes. We're going to have their components substituting in. So this becomes our component free body diagram now. And this is pretty complicated. This has 5 forces in it now. It used to have 3, it has 5 now because 2 of them just got broken into 2 components. But this is the diagram, like N cosine, N is somewhat up and somewhat to the left. So we've got the N cosine up and the N sine to the left. And F is somewhat up and somewhat to the right. So F sine thing, right? So this is our component diagram now for the situation where the block is moving down. Now, as complicated as that looks, that's been the goal of all of this. Now, again, a lot of people, you might think the system schema is like annoying or a lot of steps that you don't want to do. You might think the pure free body diagram is annoying or a lot of steps you don't want to do. But the goal of all of this is to get to F net equals MA. And the only way to get to F net equals MA is from something like this. And the only way to get something like this is from all the prior steps. We now have all the components that are lying along constituent axes. So now we're going to apply F net equals MA to each axis individually. I'm going to look at the y-axis and I'm going to do this thing, that the direct chat person was talking about like an hour and a half ago. Like anything that's pointing up, I'm going to call positive in the y-axis. And anything pointing down, I'm going to call negative. And in the x-axis, anything pointing left, I'm going to call positive, and anything right, negative. You could do it the other way around if you want. But so here we go. I'm going to apply this now. So I apply. So I do F net equals y, F net equals MA in the y-axis and in the x-axis. But also, no, before I even say that, also notice the acceleration has to, like this block is accelerating along a diagonal line. It's going somewhat down and somewhat left. So I should also make clear, like acceleration is going like this. Sorry. Acceleration is going like this. So it's going somewhat to the left and somewhat down. So it has two components. So there's a lot of components here. N got broken up, friction got broken up, acceleration gets broken up. The only thing that's not getting broken up is gravity because it's pointing straight down. So I write out, okay, N cosine theta up plus F sine theta up minus mg down equals MA sine theta. That's my vertical statement. And then I write an equally or a similarly complicated one for the horizontal, for the x-axis, N sine theta to the left minus F cosine theta to the right equals MA cos theta. Again, where am I getting all of this? Like, again, for all of you who think I know how to do the computation, but I never know how to set these things up, right, welcome to physics. Like the computation is just the math part. It's actually not the hard part of physics. The hard part is setting these things up. But how do you know to set up these equations? You don't memorize or anything. They came straight from this diagram. N cosine theta up plus F sine theta up minus mg sine theta, mg down equals MA sine theta. That is one statement from that axis. Then independently but simultaneously, we have the other statement from the other axis. Now that's a lot. What are we solving for? We're solving for A. Oh my God, the board just stopped again. We're solving for A. But what else is unknown here is N. Thank goodness we have two equations, since we seem to have two unknowns. Where did we get the two equations? From the two different axes. What are we going to do with them? We're going to have to rewrite each one of them in terms of N and substitute one into the other to get A. It's a lot of work. Are we going to do it? Yes and no. First, we're going to fix the board as soon as it actually disappears on you. But as long as you can still see it. One thing is I'm saying N is unknown and A is unknown. What about F? Remember F, friction? Friction, we learned last week, equals mu times the normal. So for friction, okay, hold on, coming back. We have 6 minutes. This board thing is driving me crazy. Or did I mention that? Okay. So we substitute mu times the normal, mu times N in for F. And mu is a given, right? Mu is known. We don't have a number for it, but it's one of the givens. So we can write these things out entirely. N cosine theta plus mu times N sine theta minus mg equals MA sine theta. That's one equation with two unknowns, N and A. And then another equation with the same two unknowns, N and A. Now, in principle, then the math, you can do the math in principle, and I might do it on Wednesday. I'll tell you right now, what I would do is I would factor out an N from each one, factor out an N. So then I would have something like N times quantity, cosine theta plus mu sine theta, minus mg equals 1, et cetera. And then I would divide both sides by that big quantity. I would rewrite each in terms of N and then substitute one in terms of the other into the other. The N's would disappear and I would have an expression for A. That is a lot of work. All of this is a lot of work, right? It's all correct. I'm not trying to waste your time or trick you. Everything I'm doing here is correct. But if it looks at all intimidating or looks like a lot of work, you're with me. You see something, it's correct, but it's a lot of work. This is and I know we have 4 minutes left. All of this, and I will finish it on Wednesday. But before I finish all of that extra algebra, since it's meant to be a physics class, let me say that the physicist way is to say, you know what? This is a lot. There's a lot of sines and cosines here because we had to break up the normal and we had to break up friction and we had to break up the acceleration. Why don't we, since we have to break things up into their coordinate axes, why don't we choose wiser axes? Why don't we actually take the Galileo of physics seriously and do what you did in the lab that you might not have realized what you were doing while we were doing? Why don't we reduce a lot of this work, follow Galileo, and choose different axes? Why don't we, that's all that said, and I know we have 4 minutes, why don't we align our x-axis with the expected direction of acceleration, i.e. tilt our axes? This is what you did in the lab. You may have understood this, you may not have. The Galileo insight is physics is going to work in whatever coordinate system we're in, but some coordinate systems are going to be a lot more convenient and productive than others. So let's tilt our head. Let's tilt the x-axis to line it up with the acceleration. And let's not say that that's a law that we always have to do that, but that's a strategy that we will always do. Because if we from here on in physics, always line up the x-axis with the expected direction of acceleration, then first of all, we won't have a cosine and a sine. We'll just have A going along the x-axis and no acceleration along the other axis, right? If we tilt our head and call this the x-axis, then it's like the problem from Wednesday, when all the acceleration is along the x-axis and along the other axis, we'll have zero acceleration. It makes the math a lot easier. Second of all, if we tilt our head like that and we line up the x-axis with this and the y-axis with the other tilt, then we don't have to break up the normal force. We don't have to break up friction. All we'll have to break up is gravity. Now, I know I have 2 minutes, but here's what I'm saying. Breaking up gravity is the part that's a little weird and confusing to people when they do that lap. It's a little bit surprising that we break up gravity because it just looks like a vertical line. It doesn't look like the kind of thing we would break up. And it's even more confusing to know which one's sine or which one's cosine. I'm giving this huge explanation to show you that even though it seems a little unnatural at first, it actually is a choice that we're doing on purpose to save all this other work. If you don't break up gravity, you've got to break up the normal and friction and acceleration. So instead, we just tilt our head and we just say, from here on, this is our x-axis, this is our y-axis, and then gravity, which is pointing straight down, is the one thing that's off axes. If gravity is pointing straight down, if you look at my picture at the bottom, gravity is not, gravity is making an angle with the plane, like the direction of the plane is making an angle with gravity, a vertical line. The angle at the top of that triangle, in other words, the angle at the top of that triangle is the angle being made between the plane and a vertical line, like we did with the normal force. It's not the original angle of the plane. The original angle of the plane is how much it's measured from the horizontal. That angle at the top of that triangle is the plane measured relative to vertical. So it's the complement of theta, just like we saw in the normal diagram. Look at that again yourself. You'll see what I'm saying. It takes a little while to sink in, but therefore it's the other angle down below in this diagram that is the original theta. So what's opposite from it gets a sine. What's adjacent, it gets cosine. So I'm just about done. I literally am just about done. That vertical line gets broken up into mg sine theta and mg cosine theta. And that's the only thing we have to break up. So if we go to original diagram, F doesn't have to get broken up. N doesn't have to get broken up. Just mg gets broken up into sine and cosine. That's where that came from in the lab. It seems weird at first, but it's to avoid all, and this is my very last page, my very last comment, and we're like 1 minute over, but I apologize if you have to go, we're just about done. If you do that, then our statement becomes so much easier. In the y-axis, we have n minus mg cosine theta equals ma, but in the y-axis now, a is 0. It wasn't under the other coordinate system, but it is here. So n just equals mg cosine theta. And in the x-axis, we have mg sine theta minus friction up. We substitute mu times the normal for friction. And I will repeat and expand all this on Wednesday, but just this is it. I mean, I'm putting the pen down. I'm putting down the cannoli, so to speak. And so we just get mg sine theta minus mu mg cosine theta equals ma. You can factor out an m, divide both sides by m. And so the answer we get is A equals g sine theta minus mu cosine theta. is a little counterintuitive at first to break up gravity. But the whole lesson today is, it's because we made a smarter choice of coordinate system to reduce the number of sines and cosines. This is Galileo in action. That's the answer to that. That's the end of that. We'll pick up on that Wednesday. You're being very patient. Yes, have a good day. All right, all of you have a good day. Thank you very much. Thank you. Sorry to. Thank you. Thank you. Have a great day. I'm stopping. Thank you. Have a good day.
Okay, Professor. So you said you wanted me to reach out